In this video, I'm going to work on two of my Sinclair systems. I will be working on a ZX81 that has a bad keyboard. I'll be replacing the keyboard with a fresh new keyboard. And on a Timex Sinclair 1000, I'll be replacing a linear voltage regulator with a modern switching voltage regulator in order to remove some heat from within the case. Hello, I am the Mighty Pez. In this video, I will be starting a project to extend the lifespan of my ZX systems for the next 40 years. So please, join me. We have two Z or ZX81 type machines right here, a Timex Sinclair 1000 and a Sinclair ZX81. This is my latest machine, just received it. However, the machine seems to power on just fine. We get the K prompt, but no response at all from the keyboard. We're going to have to take this apart and figure out what is wrong with the keyboard. So what I found when opening up the case is a rather deteriorated ribbon cable attaching the keyboard to the system with obvious breaks in it. So this keyboard was just not going to work. Also, as you can see, a lot of little parts to the broken ribbon cable were inside the keyboard connectors. So I had to meticulously remove these pieces from within the connector so that we would be able to replace the keyboard. So what I'm going to do is order a replacement keyboard membrane, and hopefully that will correct our problem. This is the keyboard that I just took out of the broken ZX81. You can see it's really kind of chewed up, and it has a broken traces right there. To compare, this is an unused keyboard of the same vintage, 1980, although the keyboard is a little bit different. This one has the rub out, whereas this keyboard has the delete button, delete key. These are the two replacement keyboards I just bought. A couple things to notice. This one is a little bit thicker, including the tape strip. So a little bit heavier, but it's obvious brand new. And I'd like to compare against the keyboard on my Sinclair 1000. I did not realize, but comparing these keyboards, it looks like this Timex Sinclair actually had a replacement keyboard at some time because it seems to better match my brand new keyboards. One way you can tell a replacement keyboard, there is a missing pixel, so you can track down the replacement keyboards here on the fast F key. In the crosshatch right there, there'll be one missing pixel that is not found on the original keyboards. But again, going back to the Sinclair 1000 keyboard, it does have that missing pixel. So that's an easy way to identify a new keyboard. Another way is to compare the color of the keyboard. The newer ones are a little brighter than the original keyboards. Other than that, they look very similar. With the keyboard connectors cleared out, I will go ahead and attach the ribbon cable for the new keyboard membrane to the system. I will go ahead and perform a quick test of the new keyboard while the PCB is still outside of the case before I permanently attach the keyboard and put the computer back together. And the keyboard does work now. I will go ahead and take the case and clean the old glue residue off before permanently affixing the new keyboard. While I'm away, I will let the system run, as now is a good time to let the ICs warm up so that I can get temperature readings to better understand the heat generation within the ZX81 type of system. Okay, we have the ZX81 running now for about 30 minutes with the case off. So I'm going to shoot some temps with my infrared thermometer, see what we get. So for the ULA, we appear to be averaging 109 degrees Fahrenheit. For the Z80 CPU, we appear to be averaging about 109 degrees Fahrenheit. For the EEPROM, we appear to be averaging about 90 degrees Fahrenheit. And for the RAM, we appear to be averaging about 92 degrees Fahrenheit. The heatsink on our power input is running about 86 degrees Fahrenheit on average. That's after 30 minutes, again with the case off. So you can imagine how the temperatures would be building up if we had the PCB sealed inside of the case right now. With the new ZX81 keyboard attached and functional, let's segue to the Timex Sinclair 1000. We are now going to pivot to the Timex Sinclair 1000 as our next project. What I'll be doing is analyzing the heat sources within the Timex Sinclair body inside of the case. I'll be analyzing the temperature output of the different ICs and different components. We'll be replacing components in an attempt to reduce current draw and ultimately reduce heat generation within the case. For this test, I've placed a temperature sensor off a data logger into the case. I've taped it up so that the probe will stay off the case itself, and then we're going to seal up the case with a little bit of tape so I don't have to keep screwing and unscrewing the case for this test. Then what we'll do is we will power on and see what the internal case temperature does. All right, the case has had time to normalize the air temperature inside. It's normalized to about 78.8 degrees. So let's go ahead and power on the unit. Okay, so we've powered on the unit. The temperature has normalized to 78.9 degrees. We're going to start our timer and we're going to keep track of the temperature. At the 15-minute mark, the internal air temperature in the case is 85.2 degrees Fahrenheit. At the 1 hour mark, the case is warm to the touch. The internal air temperature is showing 93.7 degrees. And we're going to go ahead and open up the case and shoot some internal temps. We're going to use an infrared thermometer, and I'm going to go ahead and hit several of the ICs. The ULA is showing 134 degrees Fahrenheit. The Z80 showing 134 degrees Fahrenheit. The EEPROM is shooting about 113 degrees, 112. The RAM is shooting about 100, 101, 100 degrees Fahrenheit. And the heatsink is shooting about 100 degrees Fahrenheit, depending on where I hit it on the heatsink. So we'll go ahead and power it off now. And we'll let the case cool down naturally for about 20 minutes.
The next part of our project will be to replace the 7805 series linear regulator with a Recom 5-volt 1 amp switching regulator. I will put a link to the specific device used in the video notes. This device was chosen as it will fit into the case as well as uses the existing pin layout. Thus only desoldering of the old device and soldering the new device in its place is required. In another video, I have gone into more details describing linear versus switching regulators and their trade-offs. I will also put a link to that in the notes. The short version is that the switching regulator will draw less current, in turn producing less waste heat as a byproduct within the computer, thus extending the life of the computer.
Before we start replacing this, I'm going to take some baseline notes. So first of all, I've got my multimeter hooked up so I can measure the current coming in. I also have a kilowatt meter so I can measure the current going into the power supply. The multimeter will measure the current coming out of the power supply and into the device, and we'll use that to compare after our changes. So we'll go ahead and plug the power supply in. We'll go ahead and take the power supply input, plug it in, and now we're measuring 0.295 amps or 295 milliamps current going into the power supply. Going into the ZX81. Currently we have 7 watts showing up going into the power supply and 0.09 amps going into the power supply. So those are our baseline numbers. And now we can work on replacing the 7805 linear power regulator with a modern switching power regulator.
We will desolder the 3 legs of the power regulator and remove it, as well as the heatsink so that we can add the new power regulator in its place. Unfortunately, my camera card ran out of space, so you get to miss all of the B-roll of me desoldering and then soldering in the new device. However, I can confirm that once I cleaned out the solder from the PCB holes, the new device fit right in.
After replacing the power regulator, we're going to go ahead and compare the current measurements to our previous baseline. So the first thing we notice, we're pulling the current of 141, 142 milliamps from our power supply. We are pulling 5 watts down from 7 watts, and our current coming in before the power supply is 0.07 amps or 70 milliamps. So now we're going to put the ZX81 / Sinclair Timex 1000 back in its case and go ahead and do another temperature test. I've reconnected the temperature logger back inside the case and plugged it in. So now we're going to run the data for an hour again and compare it to our previous temperature baseline before changing out the regulator. So we are at about the 1 hour mark. I'm going to go ahead, check the status. We are still recording. We're up to about 84 degrees. I'm going to go ahead and take the case apart like we did last time. And I'm going to go ahead and shoot some temperatures of the chips. Now, one thing to note, our internal temperatures are likely going to be significantly lower than the first test because the temperature probe now is further away from the motherboard and the heat generated on the PCB itself, being that we removed the heatsink that was sitting down here. So it's still valid and that the temperatures will be reduced inside of the case, but it will not be a scientific comparison.
To wrap up this project, let's look at the data collected. In this chart, we can see the results of the 1 hour heat test, both prior to and after the power converter upgrade. Compared to the baseline test, at the end of the hour, there was an approximate 9-degree reduction in the temperature measured within the closed case. Note that some of the temperature difference may be due to removal of the heatsink, which was close to the probe in the first test. Nonetheless, the improvement is plain to see. In the second chart, we can see the power metrics that have changed. Replacing the linear regulator reduced current draw by 147 milliamps, as well as a possible reduction in each of the chip temperatures. I plan on future projects with these ZX systems, including comparison of multiple ULA revisions, as well as testing a modern ULA replacement. My goal for this system is to ensure that it can operate for another 40 years. I hope this video was informative, and I do hope you will join me for future videos.